10 watts.
10 watts? Okay.
I like that.
All right, how'd you calculate it?
The force, we ended up just estimating what we think a human could push into that.
Yeah.
So we said 10 kilograms.
Okay.
Pounds.
Well, a person could probably push more though, right?
Probably could.
Yeah, okay.
But I mean, we did that and we broke it.
Oh, okay, well, good point.
To how much you can actually.
Okay.
So, sorry.
No, it's okay. No, it's fine.
5 centimeters is the travel on this.
Yeah.
So force times distance, so 10 kilograms times 9.81 meters per second squared times 5.
You have to have a time in there sometime.
Divided by time.
Cool. All right.
So half seconds.
Cool.
That's speed. Yeah.
So force times distance over time. Force times velocity. Great. All right, cool. How about another implement? Yeah. What was your implement?
We use the press chopper right there.
Okay, the nut chopper. Yeah. How much was that? Emily, I saw you working furiously chopping nuts.
That's why I work out for the day.
Yeah.
So our conservative estimate was about 6.5 watts.
Okay.
So we assumed that the stroke was based on the spring was pushing back on you, so you would use that as your baseline. So about almost 20 newtons on that, extend the spring, about a 4 centimeter stroke. And so after Emily did her little test there, she got about 50 strokes, and that took about 10.7 seconds. And so all that comes together about 6.5 watts. On the
Okay.
conservative side.
Could be about double that though, right? Because she's only putting power out in the downstroke.
Right, well, we actually have that.
Okay, you accounted for that?
So, because otherwise you don't have power to come out. So.
Great. Cool. All right. Other folks. Yeah, Johnny.
We had the French press and the leather.
Yeah. What were those?
So the French press we used just water. There was no coffee grounds in it to create a lot of resistance. With no grounds, it was 2 watts.
Okay. Cool.
And then the egg beater, again, there was no resistance. We didn't really have aims for assuming a little more 6 watts.
About half a watt? Okay. Cool. All right, some others? What was it?
Melon baller.
A melon baller, okay. How did you guys measure it?
So we measure the energy for one motion.
Yep.
Using the wave balance, like we calculated the force start of the motion and the plotted it on a force percentage diagram, and then took the energy for one stroke.
Cool.
And we kind of saw how much we could do in 10 seconds.
Great. Yeah, so we're seeing a lot of, power equals force times velocity here. That's great. And this piggybacks on our engineer's toolbox from last time, right? You're just doing these really simple power calculations, but it's giving you a lot of insight. Yeah. What was your, no, yeah.
This thing, I guess it's called the clock cam.
I think that's a grater.
Okay.
Yeah.
He's not from outer space. So we just power times torque is equal to torque times RPMs or angular speed.
Yep.
And so we measure first. We try to measure first like breakout torque.
Yep.
And then get a sense of continuous power. So our Newton meter calculations are like over there. That's actually newtons, not near meters. And then times the radius here, which is 7 centimeters. We were able to get 2.1 Newton meters of torque in a continuous operation.
Okay.
Then a couple of trials for cranks per second.
Yeah.
So we got 0.43 cranks per second and 0.66 cranks per second to be conservative. We decided 0.4. And at that times 2 pi, that gave us 5.3.
5.3, okay. Yep, and that's good. You're working off power is just torque times angular velocity. Make sure you get your units right here. It has to be in radians per second times Newton meters. Okay, any others? Yeah, okay.
We had
The second, that's salad spinner 1, salad spinner 2, okay. Yeah.
the same 10 watts.
Okay, cool. No, so this is really good. And so I wanted you, like these are all kitchen tools that require human power. So it gives you a really good frame of reference of how much is this power versus how much is this power. And there's a lot. It's an order of magnitude difference. Okay, then the next question is, how much power might you need? Could you get away with to do blender activities? Right? Yeah.
Power, I mean, you could do some sort of ratcheting thing or something. Power is a time function, so.
We're doing a blender though, right? And blender's
You
fast.
could do it in stages, right?
You-
So you could do something that like ratchets up and then blends for a second and then ratchets up and take all day.
That's a good idea.
But it's really like what's the amount of energy it takes to blend stuff up and then how much time do you have?
That's a good idea. So that's like a way to implement it. You know, you could wind up a spring, you're saying, you know, and then release it.
Store
Yep.
energy and then, you know.
But I'm talking about like, you want to do a task in the blender. How much power might it need? How much speed might it need? Right? And so this is a really good quals problem. This is like something that I'd write for the machine design quals. And so one thing that I thought about, and the reason we have almonds here, is that you might want to chop almonds, right? So, bag of almonds. And we can put our bag of almonds in here and see how it chops. And so let's check this out. So we want to know both torque, we want to know both power and speed. They both matter, right? So when we chop this, so let's chop it. Okay. Shake it. Shake it up. Okay, so you can see it's getting all chopped up. How might you figure out how fast that's going? With a stopwatch? Like, what's the rotational velocity?
Oh, I thought you meant how much time you spent.
You have some fast eyes, you know, if you could do it with a stopwatch. Well, you know, what's another way you could figure it out? Anybody, what?
Electricity is at a particular point, right? You don't have a gear to
You have to know the motor windings, potentially, to do that.
Can you read the spec sheet?
I didn't have it on the spec sheet. Any other ideas? You know, so I thought of a simple way. You can actually do it with an FFT, right? You can look at the frequency of the motor, right? And so, where's my clicker? I lost it. There it is. So, the first thing I did, let's go to the next slide, is I took an FFT. It's just an iPhone app, right? And I took the FFT and with the nuts, you get this big spike at 125 hertz, right? And so that's about 7,500 RPM. And these type of motors are usually designed to spin around like, I think it's like 6,000 to maybe upwards of 20,000. So that was kind of a gut check that I'm in the right range, right? So that's the motor speed. Okay, that's how fast the blender's going. But how could you figure out how fast you actually have to go to cut nuts with a blender? How could you figure that out? What's actually happening with the nut? Right? You've got this kind of nut in space. It's like pigs in space and the Muppets. So you got this nut in space, and you got the blade coming by it. It's hitting the nut, right? And then it's splitting it in half. Yeah?
You want an impulse because it's generally brittle.
Yeah. You need to exert a force, definitely. Yeah, and it's an impact, definitely. Right? So how could you figure out the force it takes to cut a nut? Did somebody say a knife and a cutting board? Yeah. Do we have any nuts left? I've got some in there. All right, lovely assistant. Estimate how much force it takes to cut a nut. Well, you're actuating it way back. You're feeling probably more torque than you are force. Yeah, push with that hand. What do you think?
Quarter pound.
Really? It's that? I did this last year. Oh, the serrated edge is helping you. I did it with a regular blade. You know, I wonder if you can do it kind of in the blunter edge. Oh, these are cheap nuts. Crap. Oh, well, so hand on my heart, I honestly measured this last year. And I measured actually 4.5 pounds to push a knife, like a regular kitchen knife, through an almond. I think those are like dried out. They're also salted, right, which could make an issue. No, I'm not kidding. They're actually salted. Okay. I'm not kidding. I think they're lightly salted. So it's. Anyway, I'm not going to redo my calculations because it's the thing. The message will still be correct. Okay. So up at our blender, when we're cutting nuts, we measured 125 hertz, right, for nuts. Okay. And we want to figure out how fast would this blade have to go to cut the nut. Like how fast would we actually have to spin a blender to do that? And a good, our kind of next engineering toolbox thing is just thinking about things in terms of momentum, right? So what's going to happen here is the blade's going to exert a force on the nut, right? The nut has some mass, m nut, right? And when it gets hit by the blade, it's going to accelerate. And if it accelerates hard enough, you're going to push hard enough at this point, and the nut's going to split, right? So we can define this F critical for splitting is just going to be the mass of the nut times some A critical, right? And the nuts, I put them in water, and they're almost buoyant, neutrally buoyant. But you know that the density of the nut is approximately 1 gram per centimeter cubed. And the volume of the nut is approximately 1 centimeter cubed. I did break out my calipers and measure these nuts, and it is about 1 centimeter cubed. Okay, so then from here, we can figure out that our force crit required is going to be, what I said before is about 4.5 pounds. That's 20 newtons, right? So 20 newtons equals 0.001 kilogram times A crit. And so our A crit is equal to 20,000 meters per second squared. Pretty fast. 2,000 Gs, right? Okay, so then how could you get angular rotation out of this? Angular velocity, rather. Yeah, r theta. Yeah, that's your kind of sweep, right? And you're onto that, Johnny. So what do you think the distance is where this split might happen? Right? Because if you know your distance, right, you guys remember from high school physics, deflection equals 1/2 a delta t squared plus VIT. Say the nut's stationary, delta t, so that's 0, right? We know our A. If we know our delta, like how far the nut moves maybe during this acceleration, we can figure out our time. How fast the impact is, and from that we can figure out, how fast the spinning is. So what would be a reasonable length scale here, where the nut can move? What's that? A millimeter? Well, I chose a characteristic length of the system, right? And one characteristic length of the system is actually the blade width, right? You know that blade width, the nut's going to split over the blade width, right? Because then the blade's going to go past it. So if you think about your blade, here's kind of the geometry of the blade, right? And you have the radius of the blade, which is approximately 2 centimeters, right? And you have kind of the tip of the blade, the cutting edge of the blade. And if this is 1 centimeter, right, you can say, okay, if delta is 1 centimeter, how long would it take, right? And so from this, you can rearrange it, that delta t is equal to the square root of 2 delta over A crit. And what that gives you is 10 to the minus third seconds, right? And then what you can do is figure out the critical velocity here, right? Because the blade travels this distance in that time, right? So your V crit is equal to delta over delta t, right? And then you know your omega crit is just going to be your V crit over R, right? Because you've got that velocity, that critical velocity happening out at the edge of the blade. You just divide that by R and you get your rotational velocity. Okay, so you work all that out, and your omega crit turns out to be 500 radians per second. And in English, that's 80 hertz. Cool. So what's that tell us about like how you could chop nuts? Is it possible? It means you can slow down a little bit, right? And if you slow down a little bit, maybe you need a little less power. Cool? Does this make sense to folks, like this derivation? And what I think is cool about this is like, you know, it's just starting from fundamental physics, right? The nut has a mass, and you can figure out what a characteristic angular velocity is. Okay, so the next question, though, is how would that lower speed influence our power? How could you figure that out? Yeah? Yeah? You raise your hand? Yeah, that's really good. We can start there, right? So power, and I'm going to modify force times velocity to the other one, is torque times omega, right? And what is another thing you like to do with blenders, right? Mix fluids. So the next kind of engineering toolbox here, right, is how does an object move through a fluid and how are things affected? Like how are drag forces, how do they scale with velocity? Yeah, the scale of velocity squared, right? So we got to get back to power somehow, but we know that our drag force is 1/2 times the density of the fluid times the area of the body moving through the fluid times your coefficient of drag times the velocity the thing's moving squared, right? This is a handy equation to have in your back pocket. This helps you figure out like how much drag force is on a car, right, moving through the air, and it depends on the frontal area of the car and the coefficient of drag of the car, etc. Okay, how do force and velocity and power relate? Right? We have it up there. Your power is your force times your velocity. Okay. And then we know that our velocity is omega r. And we know that our torque applied to the spindle of the motor, right, is going to be the drag force on each blade times the radius of that blade times the number of blades. That's your number of blades. Cool. So you can put this all together and you can get an expression for the power of something moving through a fluid. 1/2 NACD rho, or power of your blades moving through the fluid. R squared, omega squared. Okay. Or sorry, cubed. Okay. So then you want to think about like, okay, this thing's rated for 225 mechanical watts, right? And I would guess that when it's churning around some water, it's probably near that amount of power. It's probably near its peak power. And so what you could do maybe is look at how fast it's spinning under that peak power load, right? And see like, okay, at that we know the angular velocity, we know the power, and then we know how power and angular velocity relate, and we could see at our lower angular velocity how much less power we need. Yeah, Johnny.
This is assuming that it just goes full power all the time, correct?
Yeah, and I think when you put it on the highest setting, I would guess it's at its peak power. That's my assumption. You know, but it's not going to be at a peak power probably at a lower setting. It's really giving the most juice. Okay, so let's try that. Let's put some fluid in here. Is there a trash can? Anybody want to eat this much nuts? So, cool. Oh god, the nuts get all stuck in the bottom. This is a crappy blender.
You wanted the cheapest.
Yeah, how much? It was actually near that price point we gave in the question prompt. All right, let's clean this crap out. Okay. What's that?
You want to rinse it?
No, it's okay. You know, though, if you add particles into a fluid, it does change the effective viscosity. There's a lot of work done on that. During my PhD, actually, I used a lot of that stuff. Okay, so we have, where's the gallon of water? All right, so we can put some water in this. And you can take the cap off, too. All right, so when I did this, I put a liter of water. That seems reasonable. And we can turn this on. And I don't know if people can remember the pitch they heard. But it's about the same, right? Does that sound about the same as when the nuts were? Well, you don't have to believe me. I took an FFT with the water. And it was about the same. Right? So our fundamental frequency here was at 125. And right here it's a little bit under 125, but it's pretty close. Right? So let's say that the angular velocities are the same. What's that mean then? With the power going into the water versus the power going into the nuts? The same. Right? So the power, so we did that test, and the power of the water is approximately the power of the nuts. Okay. So that means then we could maybe use this relationship to figure out how much less power might we need with a slower blender, right? And so let's say the blender we're designing, we're gonna say all of this is approximately constant, right? You know, we're going to make a blender about that size with blades about that size that have about the same coefficient of drag and area, etc. Right? And so now we can look at the scaling relationship of this P crit over P of the blender, the real blender, power, our critical power of the blender power, is going to be proportional then to the angular velocity at critical cubed, right, over the angular velocity of the blender cubed. And this is the really powerful scaling relationship, right? That we as engineers, that means a lot to us, right? So what that means then is from that, our critical power is going to be about 60 watts in order to spin at that speed chopping nuts, right? So what's that mean then in regards to our human-powered system? It's a lot of power, right? And so, I don't know, when I see this, it makes a lot of sense why you might see that, right? You can certainly get 60 watts out of that. You can get over 100. You probably get close to the power of this, certainly for short durations. All right, so now the last thing I want to point on is just like what are the critical scaling relationships that we see here. And we saw that, when we worked out our delta t, right? Our delta t was equal to 2 delta over A crit. We can rearrange that, and we can work through that with, V crit then is delta over delta t, right? And we rearrange all that, and we see that. Plug all these in. We see that omega crit, and I'll post these notes, by the way, online. But omega crit is going to be equal to delta over r times the square root of 2 delta, the mass of the nut, over F crit. So if we're cutting nuts, right, our omega is proportional to 1 over the square root of the mass of the nut. So what's that mean for us as designers? What if you want to cut different nuts? Right? If you want to cut smaller nuts, what might you have to do? Go faster, right? And I think that may relate to why, like, I was thinking about like when the blender cuts the nuts. I think when the nuts are whole, we're really talking about this impact of the blade. But when the nuts get chopped up finer and finer, they actually tend to jam against the side of the walls. So I think it's a combination of the inertial effect of the blade hitting the nut plus the jamming that the blade has to kind of push its way through the nuts. So you can actually cut the nuts smaller than you could with just that inertial relationship. But say you put chickpeas in here or lentils, right? Lentils you might not be able to cut up. It might not be able to spin as fast, right? So that's how our critical speed may change. And then how about power, right? Our power critical is proportional because we saw this pretty close equivalent between the power to cut the nuts and the power to churn a fluid. Our power is proportional to omega crit cubed, right? Which is going to then be proportional to 1 over the square root of our mass of our nuts cubed, right? So P is proportional to 1 over mass of the nuts, square rooted, and then cubed. So we can take these two relationships then and look at how would blenders scale potentially. So if we look at the mass of the thing we want to chop over our original mass of the nuts, we're looking at the almonds, you know, and the speed of the blender versus the speed critical that we calculated, and the power over the power critical, right? And what's powerful about looking at these scaling relationships is you can see how things scale very quickly. So if we do nuts half the size, our speed has to go up by 1.4, and our power has to go up by 2.8, right? And now we're talking about 168 watts. And if we go to like 0.25, even smaller nuts, maybe lentil range, our critical velocity goes up by 2, and our power goes up by 8. And we're talking about like 480 watts. So this gives you some insight into like, you know, like the Will It Blend blenders where they put like iPhones and stuff in. Those have a few horsepower, right? Those are beefy blenders. And I suspect it's, you know, it's so you can get more of a diversity of what you can chop, right? So I think this is really cool. You know, this is what I love about engineering. You can work out some basic physics and you can get some really cool insights into, you know, what's going on, like how would things scale? Like if you wanted to make a different size blender, you know, you could maybe change, let's see, where is it? Look at all these things you could change. You could change your radius, you could change the area, you could change the number of blades. All these things affect your power, right? This gives you insight as design engineers. And I think it's important if you're going to design something like this, you should work out these type of calculations. Cool? You have any questions? People feel comfortable with that? And I'll post the notes so you can read through it again. Cool. And so I'm going to post the teams right after the class. If you're dropping, please come talk to me. And I'm also going to post an assignment today for readings from Hidden in Plain Sight. I hope you've bought that book now. And then once you meet with your teams, connect with your mentors, and then make a conference call with your partners as soon as possible. Cool. Thanks, guys. See you Monday.